In this video, we're going to be talking about all the arrows that you're going to see in organic chemistry. This is also pretty foundational to you throughout the course for OCHM 1 and OCHM 2. You're going to be working with pretty much all the arrows that you see on the screen right now. So we're going to go through, start documenting what each of these mean. So this first one, for example, this is a curved arrow with 2 prongs. So we could see that if there's 2 prongs, that means there's going to be 2 electrons moving from one place to another. That makes it pretty easy to see that this arrow right here, it has 1 prong, only 1. That means just the movement of 1 electron, designated by this E- electron. This is our equilibrium arrow. You might remember that from general chemistry. We'll just designate that EQ. This one is for resonance forms, moving between various resonance forms of the same molecule. And finally, we have this arrow which designates the movement from reactant to product. So let's look at some of these in depth, specifically this one right here. That's going to be probably one of the most important arrows to you throughout the course. Okay. This molecule right here, it's pretty interesting. We see there's a lot of different stuff going on with the electrons. This oxygen has a negative charge. This one has a double bond. Why? Well, it's not actually like that. In reality, there's kind of a half bond between each one. And that's because the electrons are constantly moving between the lone pair state and the pi bond state. So how do we indicate that? Well, our curved arrow, it always starts with the nucleophile and goes to the electrophile. Nucleophiles usually have a negative charge to them. Electrophiles may have a positive charge, may not have a charge at all. But we can see pretty clearly that this oxygen right here is going to be our nucleophile. And when we draw our curved arrows, we're normally going from lone pair to maybe a bond between another set of molecules. So we'd be forming a pi bond, or we can go, let's say we had an O right here. Let's say we had a pi bond already. We could take the pi bond and turn it into a lone pair on another atom. Okay, so in our CH3NO2 molecule here, we're going to start from our nucleophile, go from the lone pair, turn it into a double bond right here. So we're adding a pi bond to the N. When we do that, we could see that our N would now have 6 bonds going to it. And if you calculate the formal charge real quick, you would see that it would have a formal charge of 2+. It cannot have that. So therefore, we got to get rid of one of these pi bonds right here. So we're going to consider this pi bond the nucleophile, and our oxygen the electrophile. And we're going to move 2 electrons. We can visualize it, 1, 2. They're essentially just going from here over to make a lone pair. Okay, so let's take a look at what the new structure would look like. Okay, this would be called its resonance form. We would still have our CH3. We're just going to put an H3 right here. We would still have our N, but now essentially we would have a single bond to our oxygen because this oxygen received the electrons that were in the pi bond before in this area. And now this oxygen is getting its double bond because it moved some of its electrons to form a pi bond, okay? The nitrogen will still have its positive charge, and this oxygen will have a negative charge, okay? Now we see how the curved double hooked arrow worked there. If we want to indicate what's going on, we could draw a little resonance arrow which has 2 hooks on each side, okay? And we generally put closed brackets between the 2 forms to indicate that there's resonance going on. Let's talk about the single hooked arrow. You haven't seen that quite yet in organic chemistry, but you will soon, so we'll only go over it briefly. The single hooked arrow talks about the movement of 1 electron. So let's say that we have this chlorine molecule here, It's two atoms bonded together. They're bonded by this covalent bond of two electrons between them. Let's say that we split it up perfectly. We would call that homolytic cleavage. We would be taking this one electron and giving it over to its parent atom, and that one going there. And we designate it by just a hooked arrow. Kind of looks like an N. Okay, easy enough. We see the example of equilibrium arrows right here. So this is the cellular respiration equation. It's constantly moving between equilibrium, and this is just saying that the reaction is moving forward, it's moving backwards. In the instance of plants, it's basically saying that the reaction is just going between different states. Finally, let's look at this example. This is when we could see where our reaction arrow would take place, and we can get another practice with a curved arrow. We're adding sodium hydroxide to HCl, so our products would be indicated with this arrow, and we would get H2O and NaCl. Let's do another practice with the double arrow. So we're moving from our nucleophile to electrophile, excuse me. Our nucleophile is right here. So what's going to happen is that we're actually stealing the H completely. So this is an instance where we're actually ending up at an atom, not another bond. And this bond right here, the two electrons in the bond are going to go all to the chlorine. So the chlorine can have 8 valence electrons. So what we end up with is our H is still bonded to the O, but these two electrons here, now they're being used to bond the H, and we essentially get H2O. And the Na still stays as a positive, and our chlorine would now have 8 valence electrons, giving it a negative charge if you calculated the formal charge. I hope this video helped. Be sure to do all your homework problems involving curved arrows so that you don't miss any questions on the exam. Good luck to you, and thanks for watching.